Hello everybody. In this video I'll be talking about the quasi-classical matrix element now. And we would like to exclusively discuss the core argument of quasi-classical matrix element. And this quasi-classical matrix element, it basically refers I should call it, it refers to the approximation of quantum transitions. Quantum transitions. And these transitions are certainly probabilistic in nature. So we have those we have to have this quasi-classical matrix element. We would like to build this quasi-classical matrix element, and this is particularly useful when analyzing the quantum transitions in quantum systems for large quantum numbers. This is very important for large quantum numbers of these quasi-classical systems, you may call them, or semi-classical systems. Now, in this approach, what we do basically is we consider a matrix element. So what we do is we consider a matrix element. And if I assume that matrix element to be of the form n dash f of x, then n, where this n and this n dash, these are the quantum numbers. I mean, these are the quantum numbers corresponding to two different states. So n and n dash, they are the quantum numbers corresponding to two different states. And the f of x that's over here, this f of x is some operator that's representing a physical observable, a physical observable. So we have taken a matrix element, and we have written down this matrix element, and we have the bra of n dash. Then we have this f of x, and then we have n, and this n and n dash, they are basically the quantum numbers referring to the different states. Now the core approach here is that for large quantum numbers, because we are talking about the quasi-classical matrix element, so for large quantum numbers. So what happens for these large quantum numbers? The matrix element that we have, this can be approximated using classical orbits. So we can consider them as we can approximate this matrix element to the classical orbit for large quantum numbers. And the behavior of the quantum system that we have, the behavior of this quantum system tends to classical mechanics. So which is basically expressed in terms of the action variables. And this is what is called as quasi-classical approximation, or we may call it as the WKB approximation. Now, if I take down this the problem of this matrix element to a one-dimensional potential well, say I have one-dimensional potential well, okay, and its Hamiltonian is H, and H can be written as sum of its kinetic energy and the potential energy, where H is the Hamiltonian, P is the momentum operator, and then V of x is the potential energy. Now, in this quasi-classical approach, the wave function in the classically allowed region, we have already done that, and we have done that using this quasi-classical approach. And the wave function in this classically allowed region can be written as psi of x it's nearly 1 by under root of p of x, then exp of plus minus I by h bar integral p of x prime and d of x prime. So this is our wave function in the classically allowed region. And the matrix element for an operator that we have, f of x. Between the two states, which states we have? We have the state n and we have the state n dash. This matrix element can be approximated in a quasi-classical limit. It can be approximated as an integral over the classical coordinates. So if I write down this matrix element n dash f of x, then we have n, and we can approach this to x1 to x2 psi n prime, the complex conjugate of x, then we have f of x, then psi n of x. Now, in many cases, this quasi-classical matrix element is better described using action variables, and we have the classical action variable, and we have this as j equals integral of p of x and d of x. So writing down this action variable as the integral of p of x, d of x. Now let's go with an example to have more insight into this problem of matrix element. Now for harmonic oscillator, the potential, if I talk about the harmonic oscillator, for harmonic oscillator, we have the potential. What's the potential is V of x is 1/2 of m omega square x square, and we can approximate down this using this quasi-classical matrix element as in the state, say n minus 1 x and n, this will nearly be under root of h bar by 2m omega under root of n. So this is how we can exploit the matrix element to have the calculations for harmonic oscillator. And if I have to summarize this thing, in quasi-classical approximation, what we have, the matrix element that we have between the states, these matrix elements are calculated. So we had n prime f of x and then n. They are evaluated using classical quantities. That's the important point. So we evaluate these matrix elements using classical quantities such as action, that was the j of integral of p of x and d of x, and momentum. The wave functions are approximated in this case. They have to be approximated within the quasi-classical approach. And the matrix element it depends on classical quantities like action variables and the amplitude of classical, what we call as classical objects, the classical quantities, uh, the classical oscillations. So with this, we'd like to end this video where we have tried to understand uh, the applicability of this matrix element in quasi-classical case.